Hello everyone, welcome to Homework Help. If you find the videos useful, please subscribe to the channel. So in this video, we'll solve this problem using the concepts of discontinuities. So as per the problem, for each function, check for discontinuities and make a rough sketch of the curve. So we are given this rational function. So let's start by checking for discontinuities. Now in a rational function, a discontinuity can be in the form of a vertical asymptote or a hole. Now in this rational function, there is no factor that's common to the numerator and the denominator. So that's why there is no hole in this rational function. Now we can check for the vertical asymptotes by setting the denominator equal to 0. So we get x plus 5 equals 0. And now we can isolate x by subtracting 5 from both sides. So we get, so the 5's on the left side get cancelled out. So we get x equals negative 5. So this is the vertical asymptote in this rational function. Now we can check for the end behavior around this vertical asymptote by applying limits for the left side and right side of this vertical asymptote. So let's start with the left side. So limit x approaches negative 5 from the left side and x minus 3 over x plus 5. So we have to apply the limit from the left side. That means we have to use the value of x which is close to negative 5 but on its left side on the number line. So for example, negative 5.1. So if we apply x as negative 5.1, then the numerator will be a negative value because negative 5.1 times negative 3 will give us a negative value, and the denominator will also be a negative value. So negative 5.1 plus 5 will be equal to negative 0.1, and negative over negative will give us a positive value. So that means the limit value is positive on the left side of this vertical asymptote. Now we can evaluate the limit on the right side of this vertical asymptote. So x approaches negative 5 from the right side over x plus 5. Now on the right side of negative 5, we can use the test value negative 4.9. So if we sub in x as negative 4.9, so the numerator will give us a negative value and in the denominator we'll get a positive value. So the overall value will be a negative number. So that means to the right side of this vertical asymptote, so the function approaches a negative value. So now we can write the conclusion for this test around the vertical asymptote, that as x approaches negative 5 from the left side, y approaches positive infinity. And then as x approaches negative 5 from the right side, y approaches negative infinity. So there is a very important concept we need to understand and memorize. Now we can check for intercepts. So we have to check for x and y intercepts. So let's start with x intercept. So for x-intercept, we can sub in y as 0 in the given function. So we get 0 equals x minus 3 over x plus 5. And now we have to solve for x, so we can cross multiply the denominator. So 0 times x plus 5 will be equal to 0. So we get 0 equals x minus 3. Now we can isolate x by adding 3 to both sides. So the 3's on the right side will get cancelled out. So we get 3 equals x. So that means our x-intercept is 3, 0. Now we can find the y-intercept for this rational function, and for the y-intercept we'll have to sub in x as 0. So we get y equals 0 minus 3 over 0 plus 5. Now in the numerator we get 0 minus 3, which is equal to negative 3 over positive 5. So the y-intercept can be written as 0, negative 3 over 5. Now we will check for critical points in this function. So critical points are points at which the derivative of the function is either equal to 0 or undefined. Now the given function is a rational function, so we can use quotient rule to find its derivative. So we'll start with y prime equals, so we start with the derivative of the numerator, so x minus 3, which will be equal to 1 minus 0. So the derivative of x is 1 and the derivative of 3, which is a constant, equal to 0, times the denominator and then minus the numerator expression x minus 3 times the derivative of the denominator, which will be 1 plus 0 over the square of the denominator. Now we can simplify this expression. So in the numerator, 1 minus 0 is just 1. So in the first part, we just get x plus 5. And then in the second part, 1 plus 0 is just 1, and x minus 3 times 1 will just be x minus 3. So it won't change. So we can just distribute the negative sign into the parentheses. So we get negative x plus 3 over x plus 5 squared. Now we can simplify this expression. So the x terms in the numerator will get cancelled out. So we are left with 8 over x plus 5 squared. So now we have to look for critical points. So for that we have to set the derivative equal to 0 and solve for x. If we set the derivative equal to 0, there are no x values that will make this fraction equal to 0, because when we cross multiply the denominator, so we just get 0 equals 8. So that means, so there are no critical numbers at which the derivative is equal to 0. So now we have to find the x values at which the y prime is undefined. So those are x values at which the denominator becomes equal to 0, and in the denominator we have x plus 5. So if x plus 5 is equal to 0, then we subtract 5 from both sides. The 5's on the left side get cancelled out, which is equal to x equals negative 5. Now this is where the vertical asymptote is that we have already found. So we have already also found the end behavior around the vertical asymptote. So we do not need to analyze this x value again. So we can conclude that there are no critical points at which y prime is equal to 0. Now we can analyze the horizontal asymptote and the end behavior around the horizontal asymptote. So for that, we'll have to modify the given function. So I'll use a different color now. So the given function is y equals x minus 3 over x plus 5. Now in order to find the horizontal asymptote, we'll have to analyze the degree of the denominator. So the degree of the denominator is equal to 1. So that means we have to divide each term in this rational function by x raised to the power which is equal to degree of the denominator, which is x exponent 1, which is equal to just x. So we'll divide each term in this function by x. X over x minus 3 over x over x over x plus 5 over x. Now we can simplify this expression. So x over x is 1 minus 3 over x, and in the denominator x over x is 1 plus 5 over x. Now we can apply the limit equation of the horizontal asymptote. So x approaches infinity, then 1 minus 3 over x over 1 plus 5 over x. So we can apply the limit separately to the numerator and the denominator. So limit x approaches infinity, then 1 minus 3 over x over limit x approaches infinity, so 1 plus 5 over x. So now we can sub in x as infinity, so we get 1 minus 3 over infinity over 1 plus 5 over infinity. So we know 1 over infinity is equal to 0. So the second terms in both the numerator and the denominator go away. So we are left with 1 over 1, which is equal to 1. So the horizontal asymptote is at y equals 1. Now we can find whether the curve is approaching the horizontal asymptote from above or below. So for that, we can apply the limit to the given function on the left and the right side for a big value of x. So let's start with the left side. So we can apply the limit x approaches negative 100 and then x minus 3 over x plus 5. So we can sub in x as 100 by applying the limit. So we get negative 100 minus 3 over negative 100 plus 5. So in the numerator we get negative 1 over 3, and in the denominator we get negative 95. Now if we evaluate this fraction, we get a value greater than 1. Now we want to reference this value with respect to 1 because the horizontal asymptote is at y equals 1. So this is greater than 1. So that means the graph approaches the asymptote from above the asymptote. Now we can calculate the limit on the right side of the number line. So limit x approaches positive 100. So x minus 3 over x plus 5. So we can apply the limit and sub in x as 100. So 100 minus 3 over 100 plus 5, which is equal to 97 over 105, which gives us a value less than 1. So that means on the right side of the x-axis, the graph approaches the asymptote from below. So the curve is below the asymptote. Now we have to use all of these characteristics about this rational function to make a rough sketch. So we can start with the vertical asymptote. Now the vertical asymptote is at x equals negative 5. So let's assume it's here. Negative 5. Now we can show the vertical asymptote. Now we can show the end behavior around the vertical asymptote. So on the left side of this vertical asymptote, so the function approaches positive infinity. So the end behavior can be shown like this. And on the right side, the end behavior can be shown like this. Now we can show the intercept. So the x-intercept is 3, 0. So let's assume it's somewhere here. And the y-intercept is 0, negative 3 over 5. So let's assume it's somewhere here. So next we can show the horizontal asymptote, and the horizontal asymptote is at y equals 1. So that will be somewhere here, 1. And now we can show the end behavior around the horizontal asymptote. So on the left side, the curve approaches the horizontal asymptote from above. So we can move this end behavior somewhere here. So that means on the left side of the vertical asymptote, we can sketch the curve like this. So we can see that the curve is approaching the horizontal asymptote from above on the left side of the x-axis. And on the right side, the curve has to approach the horizontal asymptote from below. So we can just extend our end behavior to the right side of the vertical asymptote through the y-intercept, x-intercept, and then close to the horizontal asymptote. So this can be a rough sketch of the curve. So these are the steps you have to keep in mind to solve a problem like this one. So I hope you'll find this video useful. Please share it, like it, and subscribe to Homework Help. Thank you very much and have a nice day. Bye.